Hi everyone, it is a great pleasure to be here with you today. My name is He Bo. I'm a PhD student from Beijing University of Posts and Telecommunications. The paper I will be presenting today is titled DeepHop on Edge, Hop-by-Hop Routing by Distributed Learning with Semantic Attention. In this presentation, I will begin with the introduction of the routing in edge networks and the challenges in the scenario. Then I will elaborate our distributed routing framework, DeepHop, and its methods, including hop-by-hop approach, multi-agent reinforcement learning, and the semantic attention mechanism. Next, I will show our experimental results. Finally, I will conclude this paper. First, I will introduce the routing problem in emergent edge networks. As an essential component of 5G networks, multi-access edge computing provides benefits of low latency, mobility, and location awareness for communication networks. However, traffic data in edge networks are influenced by many factors, such as time, emergency, random loss, location, and the energy of various terminal devices. To cope with the dynamic traffic on complicated edge networks, an effective routing mechanism should be resourced. Currently, many efforts which have been paid to solve the routing problem in edge networks relied on complex rules and environment modeling. But there still exist some challenges that have not been completely solved. First, it is hard for the traditional four-pass routing, which depends on the neighboring discovery and the network state updating, to handle the unexpected traffic stress on distributed edge nodes. Second, the traffic fluctuation from autonomous vehicles or cloud-carried smart devices like virtual reality leads to some elements of the network state exhibiting great variations. Thus, the heuristic centralized routing can hardly capture the global dynamic network state transitions. Third, network state elements like traffic requirement, destination, link state, and network topology have different significance for routing, but their implications are intractable to be distinguished and utilized reasonably in the traffic data forwarding process. Then I will introduce the proposed DeepHop framework that intends to solve the routing tasks in distributed edge networks. Let's take an overview on the contributions that are proposed to solve the previous three challenges. To address the first challenge for traditional four-pass routing methods, we adopt a hop-by-hop approach based on the distributed edge nodes. To address the second challenge, we use multi-agent deep reinforcement learning method to capture the global dynamic network state transitions. As for the third challenge, we utilize the self-attention mechanism to help agents understand the effect of each network state element. Besides, we propose a new algorithm to optimize the policy. This is the illustration of the routing mechanism in a single edge node. As shown, a node receives an input packet and obtains its QoS requirements and the destination node. Then the agent determines a next hop node for the packet according to the packet information and the network state, such as latency, packet loss rate, RTT, and so on. In this way, packets are transmitted between edge nodes in the hop-by-hop approach. There are two objectives. One is minimizing the ratio of discarded packets, which means reducing the packet loss. The other is minimizing average slowdown of each packet, which means reducing the delay of all packets. Now I will give a brief introduction of the deep reinforcement learning. A DRL model is built on the Markov decision process. As shown, an agent receives a state from the environment and determines which action to take. Then the agent receives the reward of its last action and the next state. In DeepHop, we adopt multi-agent deep reinforcement learning so that the agent nodes run DRL models in parallel as listed in algorithm 1. For each DRL model in an edge node, the state space including the destination node, node state, link state, and the packet parameters. As for the action space, an action is defined as selecting a candidate next hop node. The reward function contains the changing distance to the destination node, the number of current waiting packets, and whether the packet can be transmitted to the next hop node successfully. Apart from the method, we propose a DRL MADRL algorithm called MAPOKTR. The algorithm aims to achieve the monotonic improvement of the decision-making policy. In each epoch, we calculate the ratio of probability distribution and the point probability distance between the current policy and the policy in last epoch. And the algorithm utilizes the two distance measurement in the loss function to optimize the DRL policy and accelerate its convergence. As introduced before, the environmental state is a synthesized vector of one dimension. Each agent has a complicated state space and needs to receive three state elements. Although the elements are jointly input to the neural network, they have different impacts on the decision-making process. Therefore, we build fully connected sublayers of neural networks and assign one to each state element. The structure helps the neural network to distinguish different elements and learn the dynamics of each element independently. In addition, each state element has different importance. For example, forwarding to the destination is the basis of decisions about routing, so that it should be assigned more weight. Thus, we propose semantic attention mechanism, using the attention mechanism to assign weights to corresponding sublayers and accelerate the training process. The attention mechanism dynamically pays attention to certain elements of the input, which helps the agent to perform the task effectively. In summary, the training process of DeepHop with the new algorithm and SAM is exhibited in algorithm 2. Next, I will exhibit the relative experimental results to prove the contributions. Before that, I need to introduce the dataset and the experimental environments. We implement DeepHop on Ubuntu and use PyTorch to construct the neural networks. We select two real-world online network topology graphs from the Internet Topology Zone. Then we build experimental edge networks based on them as Net 1 and Net 2, which contains 12 and 20 nodes. The traffic packets used in our experiments come from an open real traffic dataset, TOR. In each episode, 80,000 packets are injected to the network. In experiments, we change the speed of data injection, that is, the number of packets injected per second, to cause different degrees of network congestion. First, To explore the impact of routing rules, we compare the hop-by-hop method in DeepHop with a routing protocol of edge network (CRF) in Net 1 and Net 2. The experimental speed of injection are 3,000, 4,000, 5,000, and 6,000 traffic packets per second for covering different degrees of network congestion. To compare the routing performance, we defined a metric called TUR as the ratio of the packets being discarded before reaching their own destination nodes. Table 1 exhibited the TUR results of the two methods. It is obvious that DeepHop handles the routing task better under all degrees of congestion in edge networks than the heuristic CRF. Moreover, DeepHop performs more stably than CRF in low degrees of congestion according to their results in Net 1. Second, we evaluate the performance of the different algorithms on routing. In experiments, agents adopt the MAPOKTR algorithm to learn the joint optimal policies. We compare it with MAACKTR and MADDPG algorithms. In each chart of experiments, the x-axis denotes the first 2,000 training episodes of the models, while the y-axis notes the TUR obtained by the models in each episode. It can be seen that the MAPOKTR algorithm has obvious advantages over the others under all degrees of congestion in networks with different size. As introduced before, DeepHop keeps the semantics of elements and separately inputs them to sublayers of the attention mechanism. Hence, the structure of SAM used in the agents of DeepHop, labeled as SA, MADRL SAM, is evaluated. For comparison, we also make experiments using the structure MADRL SM and MADRL. It can be seen that the structure of separated sublayers makes the neural networks understand the semantics effectively, and the attention mechanism accelerates the convergence of policies. Next, it is required to evaluate the effect of the reward function. We explore the effect of each element in the completed reward function and use reward 1, reward 2, reward 3 to denote a function including different elements respectively. It can be seen that the completed reward function obtains the best performance under all degrees of network congestion, and the elements of the reward function are all proved to have a policy effect when the agent learns to handle the routing tasks. Last, we test the DeepHop capability of dealing with the case where the congestion degree is highly dynamic. To generate time-varying network congestion, the number of injected packets are randomly selected from 3,000 to 6,000 per second. The figure shows that DeepHop can cope with the time-varying network congestion, so that DeepHop has a good robustness and it is suitable for actual edge network environments. Finally, I will briefly summarize the main issues. In this paper, an adaptive and online framework, DeepHop, is proposed to cope with the routing tasks in edge networks. DeepHop utilizes the multi-agent deep reinforcement learning to determine hop-by-hop routing for traffic packets and deploys the agents on edge. To learn the semantic of complicated observation elements, DeepHop designed a semantic attention mechanism to help the DRL agents learn better policies faster. DeepHop adopts a novel MADRL algorithm, MAPOKTR, which introduces the point probability to its loss function for keeping the policy being multinomially improved. For the future work, we will further explore the communication between the agents on nodes and solve the retrain problem of MADRL model when the topology of edge networks changes significantly. This is all for my presentation. Thank you very much.